Hello, fellow colleagues. My name is Chris Lopez. I'm going to be presenting the Lisp hardware architecture. It is based on a MIPS-1 instruction set architecture. First, we're going to go over the design overview for how we implemented the MIPS-1 architecture. So it is a load store architecture, which is also known as a register-to-register architecture. It's more fitting of a name because it implies that every instruction only works on CPU registers with the exclusion of load store instructions. It is also a reduced instruction set computer, which it only operates on one instruction per cycle. We have the instructions are going to be fixed 32 bits for each format that we include. Regardless of how many bits are going to be needed, they will all be 32 bits. Luckily, there are only 3 formats within the instruction set architecture itself, which are a register type, an immediate type, and a jump type. As far as the addressing modes go, we've included 3 different addressing modes for the architecture. We have an immediate mode, which allows us to get the operand from the instruction itself. We have a register mode, which allows the instruction to specify a register address from the CPU register, and a based indexed, which allows us to specify a value of specify a register that holds the contents of an effective address, which gets added to a value in the instruction itself to calculate for the effective address for memory grabs. Now, when it comes to memory, we have opted for a Harvard architecture. We didn't use it von Neumann because von Neumann would require us to have some kind of memory management so that the instructions and the data do not conflict with each other inside the same memory module. So having this separate data and instruction memories allows us to not worry about this as we develop the hardware architecture for the CPU. Now, our data memory and our instruction memory are instantiated created using the same memory with the same controls. We have they are both a 4K by 8 deep, which are word addressable and formatted in Big Endian. Big Endian being where the most significant byte is stored in the least significant address location, and then every subsequent less significant byte is stored in the more significant address location. And then with our memory being 4K by 8 and our instructions being 32 bits in width, this allows us to hold up to 1K instructions, which will be more than enough to verify the design of our CPU. Now, when processing the data, since we only have 3 different types of formats for the instructions, we wanted to be sure that we didn't have 3 different logical units to be able to process each individual type. So we opted for using this ALU here, which uses a 5-bit field to specify one of 32 operations that can be handled on the actual instruction itself. We have arithmetic operations, logical operations, and other operations, which are non-categorized, which allows us to do a variety of things of what's included in the architecture for a MIPS-1 based processor. Now, when handling the instruction sequence, we know that one of 3 types are going to come in. So each format has its own layout with its own specified fields, which makes it very nice and easy to handle to split up when it comes to our instruction unit. So within the instruction unit, we have a program counter, which in itself is self-incrementing as long as we have this PC load or PC increment wire high, so that it'll self-increment after every clock, allowing the instruction memory to be accessed at every sequential location. And then for the PC control, we also have a load signal in case you wanted to have any jump or branches. This allows the PC to get loaded with a branch or a jump location so that memory can get access for those instructions. When memory is accessed, it then goes into this instruction register, which is 32 bits in width, with the IR load high to actually signify it wants to get the next instruction. And from the IR, it is going to send out the bits to their appropriate locations. They're always going to be split up in this manner, meaning this sign extended is always going to sign extend the lowest 16 bits, regardless of if it's the function and shift amount or if it is actually the immediate value. But that goes into how we need to control the bits of what's actually getting used. So that's where we get into our control unit. The control unit first checks the upper 6 bits to see if they are zeros. If they are, then we then look at the lower 6 bits to see if what R-type operation it wants to complete. And then we look, if it is not 0, then we know that it has to be either an I or a J-type, which in that case we'll look at the upper 6 bits and determine which instruction it will execute. Now, when it comes to our control unit is a multi-cycle architecture. For the controls, for the multi-cycle, we have one instruction is completed per cycle, and then each cycle takes multiple states. And then, depending on the instruction, they vary in state length. So one instruction could be three states, and another instruction could be 6 states. On the right-hand side, you'll see that we have all 3 types here. All 3 types are going to go through the first 2 states, which are fetch and decode, and then the execute state is what's actually going to vary from type to type and from instruction to instruction. And then after it executes, there will be a write back state, which will then go to the back to fetch.
So you indicated one took 6 states, one of your instructions?
I was just saying, for example.
Oh, for example.
Yeah, they could take multiple states. It could be 3, 4.
Yeah.
Yeah.
Did any take 6?
I don't think so. I don't think we implemented any enhanced that had any.
Okay.
Okay. And so when it comes to verifying the design, the first memory module that we had is we were given 14 memory modules to verify the design of our hardware to see if they could actually process the sequence of instructions. So this first one is a beautiful example of it working because it allows us to then be able to set up programs that will verify every other instruction. Within the first memory module for the instructions, we have an R-type addressing mode. You can see on the top left here for the Louis instruction, which addresses to R0 and let's see, right here. The 02, that's the operand grabbed from CPU register, and then on the right hand side here you'll see that we have their immediate value being accessed from the instruction itself, and then towards the bottom we have the store word, which is going to use our base index, which grabs the contents of R13 and adds it to 0 to calculate the effective address of where the contents of R1 are going to be stored. You can see here that R13 is loaded with 100.100C0, which since our address is only 12 bits, it only grabs the lower 12 bits, which will be 0C0. And we can see here on the left-hand side that the contents that are in R1 is 1, 2, 3, 4, 5, 6, 7, 8, and that gets stored into 0C0. Within every page that we have the verification, we have included boxes that are going to show and highlight the individual instructions and how it verifies them. As far as future capabilities, MIPS 1 does allow for half byte, byte, and other addressing modes that our memory does not allow for. Our memory architecture only allows for word addressing, and with a 12-bit a 12-bit address bus, we are allowed to access pretty much any one of those address locations. So we do have the capability of loading that byte addressable memory, but we are not taking advantage of it. So that would be definitely one thing that we would advance on. Any questions?
Okay, good job, Chris.